These are the notes on forces. A force is a push or a pull on an object. So we've already seen some examples of forces like gravitational force, but now we're going to be talking about all the different forces and how they sometimes balance each other and how sometimes you have a little extra net force in one direction and how that affects the movement of objects. But basically, it's either pushing something or pulling something. Or to put it another way, a force on an object, a push or pull is. So a force is defined as a push or pull exerted on an object. Forces can cause objects to speed up, slow down, or change direction as they move. So those are the possible results if you have a net force. Okay, or the other option is forces could just be balanced and you don't see any change to the object. Based on the definitions of velocity and acceleration, a force exerted on an object causes that object's velocity to change. That is, force causes an acceleration. Remember, that's Newton's second law, F equals ma. Look at a book lying on your table, maybe your textbook. And there's different ways you could move that. You could just push it along to get it out of the way, or you could pull it toward you. You'd have to exert force on it to do that. Another option would be to get a string, tie it around the book, and pull the string. Another option would be to push the textbook with a ruler or a stick, and all of those would be examples of contact forces because they are coming into contact with the object, exerting a force on it. It's something touching the object, providing a force. Now, if you were to take that textbook off the table and drop it, well, now it will be acted on by a different force, a force that is not in contact with it, at least until it hits the ground, and that is called a field force, in this case, gravity. So we've already been dealing with field forces, actually, we just didn't refer to them by that name. A field force is exerted without direct contact. So another example of a field force would be magnetism, electromagnetism. So if you have two magnets that are near each other but not touching, each of them exerts a magnetic field force on the other, and that can either cause attraction or repulsion depending on the way the magnets are configured. So that would be another example of a field force. Every force has an agent, something causing the force to occur. It could be you pushing on the textbook. It could be the earth pulling on the textbook downward. If you want to show all the forces acting in a system, you need to draw a free body diagram. We're going to be seeing a bunch of these. This is the way that we think about all the different forces acting on an object in physics. We have already discussed Newton's second law to some extent. Newton's second law is basically a statement that objects will be accelerated in a way that is proportional to the force exerted and inversely proportional to the mass of the object. In other words, the more force, the more acceleration, the more mass, the less acceleration. Okay, this is one way of writing Newton's second law. But what we didn't talk enough about yet is that that means the net force. So if you talk about all the forces acting in a system, you have to figure out which forces are balancing each other. Very frequently, many forces will counteract one another, and so that they sort of cancel out. So what we need to figure out is what is the net force acting on an object. After canceling out all the forces that cancel, what is the remainder and which direction is it pointing? And then that will indicate which direction we should expect there to be acceleration. So this is really just a modified version of Newton's second law. A equals F divided by m. That's acceleration equals force divided by mass. The regular way that we write this is the more typical way, is F equals ma. This is one I would like you to remember, not just for this course, but just in general for the future. This is a good equation to know, just to memorize. So if you ever want to know how much an object will be accelerated, and if you know the force and the mass, you can figure it out. Or if you know the mass of an object and how much it's accelerated, well, then you can determine the force, right? Or if you know the force and acceleration, you could actually determine the mass of an object. That is one way that we determine the mass of unknown objects. So basically, this equation is saying the more force, the more acceleration. If you double the force, you double the acceleration with the same object. But if you have different objects, well then, the object with the most mass will have the smallest acceleration. The object with the least mass will have the greatest acceleration. You probably are aware of this in your everyday life. If there's a box on the floor and you want to push it, pretty easy to push a box on the floor. But if you want to push a bookshelf full of books, well, that's a lot harder. It requires a lot more force to move it the same amount, or let's say to accelerate it, okay, to get it in motion. So this is sort of obvious, but it's very, very practical, very, very useful. So 1 unit of force causes a 1 kilogram mass to accelerate at 1 meter per second squared. So the units that we use for force are 1 kilogram meter per second squared. That's at the bottom there on the left. But that's very ugly. That doesn't look very elegant. So as we've done in many cases, when there is a unit like this that is so critical, like for studying forces, they decided to give it its own name. They named the unit, and of course they named it after the great scientist who contributed so much to understanding forces, Newton himself. So we called the unit the Newton. So 1 kilogram meter per second squared, you probably don't want to write that. You'd probably just rather write a capital N that stands for Newton. And that is the unit of force. Speaking of Newton, his first law states, an object that is at rest will remain at rest. An object that is moving will continue to move in a straight line with constant speed if and only if the net force acting on that object is 0. So I've worded this another way. I've reworded this. So look, I think this might be a little simpler way of saying it. Objects resist changing. They keep on moving or staying still unless they are literally forced to change. Now, when we're talking about force here, we are talking about the capital F, we're talking about force, and we're talking also about net force. Because as you are going to see, many times there are lots of forces, but a lot of them will actually cancel out. Another way to say Newton's first law in one word is inertia. Inertia is the resistance something has to changing. So Newton's first law is sometimes called the law of inertia. Inertia is the tendency of an object to resist change, just as I said in my briefer definition of Newton's first law. So if it's moving, it'll just keep on going unless something stops it. Okay, if it's standing still, it's not going anywhere unless something, puts force on it, net force, getting it into motion. It's a very simple idea, but it's very important in physics. Now, what kind of forces are we talking about? Well, there's many, many, many different kinds of forces, but these are most of the ones that we typically deal with in like a high school physics class. There is the force of friction. So depending on how much time we have, that's usually what determines how deep we get into friction. Because friction has a whole bunch of considerations that go along with it. There's static friction and kinetic friction, and then you have to deal with the slope. So we will be dealing with this at least a little bit, okay? But that can be a major consideration in a real world calculation. Another one is what we call the normal force. Remember what normal means? Where that came from? Not normal like not strange or just ordinary, but normal as in 90 degrees. That's what it means. 90 degrees to a surface. So this gets a little tricky sometimes when you're talking about rough surfaces. And if you think about what do things look like on a microscopic level, but for the most part, we're dealing with flat surfaces that on a macroscopic scale, you can easily find the normal, which is the perpendicular to the surface, okay? So normal forces are often counterbalances of the force of gravity, okay, the weight. The next one is the spring force. We sometimes write that as F sub SP. As the subscript, we write SP. And a spring force is a restoring force because springs like to stay at their regular length. If you stretch the spring longer, it wants to go back, and the force is to pull things together. If you try to squeeze a spring smaller than its regular length, then it actually wants to go outward. It pushes back. It wants to get back to the way it started. So it's a restoring force. Depending on which way it's going, it's doing the opposite of the direction of motion. Okay? It's a little more complicated than that, but that's a quick overview. Then there's the force of tension. If you have a rope or a string and you're pulling on it, usually it has to be taut. Okay, there has to be something on each end. Okay, one end is where the force is being applied, and it can transfer the force all the way through. Now, tension depends on elasticity, but for the most part in high school physics, we usually just assume that all the ropes and cords and strings don't stretch, that they stay the same length, and that they don't break. Because if that happens, well, that can mess up our calculations. Then there is the force of thrust. Thrust is when you push, okay, behind you, and the object goes in the opposite direction. Forces applied that move rockets, planes, and cars. Okay, so the force of thrust is actually applied in the direction the object is moving. And then we have the force of gravity, Fg, which is really your weight. It's the force due to the gravitational field between the Earth and whatever the object is. And of course, the force of gravity goes downward toward the center of the Earth. It can be way more complicated if we get into details, exactly where you are if you're not on the surface of the Earth, but for the most part, our calculations are going to be dealing with regular old lowercase g Earth gravity. So we use the word normal today to mean typical, common, and the reason it means that today is because it sort of meant the things that follow the rules, in conformity with the rule. But originally the word normal comes from the Latin word norma, which was literally a carpenter's square. You can see a carpenter's square pictured here. There's actually two of them. Okay, and a carpenter's square is used for making sure that the corners of a room are at right angles, okay, 90 degrees. And this was so important in construction to get that right that it lent its meaning to many other things. And there's even a constellation in the southern hemisphere called Norma. Okay, we don't get to see this in California, but if you ever go near the equator or south of the equator, you can see this little tiny constellation, and it's called that because it looks like it has pretty close, not exactly, a right angle there inside the constellation. So anyway, we call it a normal force because it acts at 90 degrees to a surface, just like a carpenter's square. If you put one side flat on a surface, the other side would point straight up at 90 degrees. So Newton's second law of motion is usually written F equals ma. But remember that gravity is just an acceleration. So we can also write it F sub g, which is the force of gravity, equals mg. This is something we use all the time. This is a force that we're always feeling if we're on the Earth. So this is included whenever you're doing a free body diagram showing all the forces acting on something. You're going to have this as one of your forces. Okay? So it's not always causing the object to move. Even if you're stationary, you are still being acted on by this force. Okay? A lot of times there are balancing forces, very commonly the normal force, that prevents the acceleration, but you still have to consider the force of gravity. Another name we have for this is the weight. So you can calculate the weight of something by multiplying its mass, which is how much stuff it has in it, times gravity, times Earth's gravitational field. Boom, that's the force acting on an object caused by gravity. So we use this calculation all the time. This is really from Newton's second law. It's a variation on Newton's second law that the weight force, or Fg, the force of gravity exerted on an object, is the mass times little g. So here's an example of a free body diagram where we're just showing the forces. These are force diagrams showing all the forces acting on an object. This is one of the easiest ones because in the case of a basketball that's up in the air, okay, there's nothing touching it, and as long as it's not magnetic and there's no magnetic field operating, the only thing that is providing force on that ball is its weight, okay, the Earth's gravitational field. It's a field force. Remember, if nothing is touching the object, then the only things that could really be acting on it are field forces like gravity or electromagnetism. Okay, so the only force acting on that ball is the force of gravity, and that causes its weight, that is a measure of its weight. And you can see that if the ball started at the top there where there's that little V with a dot, and then the acceleration that gravity causes is going to make it move faster and faster with each subsequent moment. It's going to go faster and faster. But that's just acting due to one force. That's just one force acting on the ball. So it's a pretty easy calculation to make. You can tell where that ball will be in the future just based on the acceleration that will occur due to the force of gravity. So why am I so down on weight all the time? It's not really that I'm down on weight. I just think weight is not a true measure of the properties of an object. Weight depends on so many things, and it's kind of what I would call wishy-washy. But we often need to know it in physics. In chemistry, we very rarely need to know the weight, and a lot of things in chemistry that are called weight are actually masses. Okay, like atomic weight, well, that's a mass. It's the weighted average. That's another expression. So anyway, I don't want to get into that. So a lot of times you may think, wow, he really doesn't like saying the word weight. Well, I do when it's the correct word. And when we're talking about the force of gravity acting on an object, well, that is the weight. So now would be the correct time to use that term. So we sometimes measure weight with springs. And the way that we do this is, you know that if you're standing on a scale, like this guy is here, standing on a scale, you know that the force that he's pushing down with has got to be counterbalanced by something because he's not accelerating, as long as he's not actually moving at the moment. That's why we wait a second after we get on a scale before we read off the weight, because you have to get to the point where you're not moving, not accelerating at least. So the spring has to push up with the same force that he's pushing down, and they can measure that, and that's really what you're getting on the spring. You're actually getting a measurement of the spring force pushing upward, which is exactly opposite but equal to the gravitational force, which is your weight pushing downward. But don't be so sure that that's going to be your actual weight or the force that gravity is pulling on you. Because what if that guy isn't just in a regular room? What if he's in an elevator? So if the guy's in an elevator, well, it depends if the elevator is moving, doesn't it? It actually doesn't matter if the elevator is moving. He would get the same measurement unless the elevator were like accelerating. So in order for an elevator to begin moving upward, well, to go from not moving at all to moving upward, there has to be at least a momentary acceleration. They don't make it too fast because that's really jarring. So it's usually the first, let's say, half a second, sometimes a second, that the elevator begins moving. During that period, the elevator is accelerating. And look at what happens. If the elevator is accelerating upward, well, wait a second. So the spring force that's pushing up on the man, which is actually what you're reading on the scale there, is counteracting both the force of gravity and the acceleration due to the motion, because he's being pushed down because the elevator floor is accelerating up into him. So he would get a higher reading on his scale. The same thing goes if the elevator is moving downward, at least when it begins to move downward. At that moment, well, it's almost like the scale is being pulled out from under the man's feet, which at least during the acceleration would lower his apparent weight. So this is just one of the ways that weight can be wishy-washy. You can get a false reading if you're in an accelerating reference frame. These are called accelerating reference frames. Now, once the elevators don't keep accelerating the whole way, because if they did, they would be going faster and faster and faster, maybe break through the ceiling and fly through the air. Again, Charlie and the Chocolate Factory reference here. But they accelerate for a short time, get it moving, then it mostly goes at the same velocity. Then it actually has to accelerate again in order to stop. Think about it. In order to go from a moving elevator to a stationary elevator, it has to accelerate again, but in the opposite direction. And you would also get an effect on your scale reading. Okay? So just keep in mind, weight, one reason weight can be wishy-washy is because you have to know if you're in an inertial frame. An inertial frame is a frame that is not accelerating. So if you're going at a steady velocity, okay, like the Earth is in an inertial frame because we're not speeding up or slowing down. So that's why these things are not affected by the motion of the Earth. But elevators will affect them, so think about that. Of course, we can't forget about Newton's third law. For every action, there is an equal but opposite reaction, and that is the regular way that it is stated, and it's very clear. Yeah, well, actually, we've already been talking about it, haven't we? Because normal forces, I said they're often a reaction to the force of gravity, the weight, and we also talked about spring forces. Yeah, those are all kind of examples of Newton's third law, aren't they? And even when you get on a balance, the spring force, which is exactly opposite the gravitational force, these are all examples of Newton's third law. And you could state it a little more simply than this, I guess. Action, reaction. So there is a very practical upshot to Newton's third law, something that will save you endless troubles when you're considering the forces acting on an object. Now, first of all, when we represent an object, it's a lot easier to represent it with a point or a small sphere than to always represent the shape of the object itself. Generally, this sphere will be put at approximately the object's center of mass, ideally exactly where the object's center of mass is. So here is our physics textbook. Now, our physics textbook, if you've ever picked it up, I hope you have, you'll know that it has some mass. Any object that has mass that is on the Earth or anywhere else with a gravitational attraction, anywhere else where there's something nearby, will have a weight. Okay, the force of gravity acting on it. That is its weight. Okay, but look at that textbook. Is that textbook accelerating? Since that textbook is not accelerating, it's actually just apparently just sitting there, lying there on the shelf, we know that that must be a balanced force. Because remember, imbalanced forces, a net force causes acceleration. F equals ma. So you could deduce, and this is how the force was discovered, there must be some other force, some normal force acting perpendicular to the surface of that table that is exactly balancing the force of gravity. So what is imparting that normal force? Well, you could think of it as the shelf pushing back. The book is pushing down, the shelf is pushing back. That is Newton's third law. Equal and opposite reactions. Action, reaction. So if the weight is the action, then the normal force is the reaction. And it's very simple to understand in this context. Here, from a slightly different angle, imagine that textbook definitely has weight. Not a whole lot. It's not super thick, super heavy. But it's not accelerating. So it must be balanced by another force. That is the normal force. Remember, normal force means at a right angle to a surface. Okay, so the surface, because that's a horizontal shelf, the normal force goes straight up. The force of gravity goes straight toward the center of the Earth, which is the center of mass for our planet. And we know those are balanced because there's no acceleration. Here's the tricky part. Even if that textbook were moving at a constant velocity, the forces would still need to be balanced. Because remember, a net force causes acceleration, not velocity. So sometimes it's a little less obvious when there is a moving object that the forces can still be balanced. A classic example is a tug of war. If you've got two different groups of people, it doesn't matter if they're the same mass, actually. It depends on how much force they're imparting to that rope. Okay? So if they're both imparting the same amount of force in both directions, then the rope doesn't go anywhere. It's a tie, it's a draw. Obviously, when the forces are imbalanced, you begin to get an acceleration, which is what leads to the people on one side falling over. But in this situation, what we see is neither side is winning. Therefore, between the four different people on each side imparting the force, the net force on that rope is zero because you have equal amounts of force to the right and to the left. So that is the end of the notes on forces.